Now forgive me for having the layout of this page a little bit different than what's on your set of lecture notes. It didn't scale well to what we were doing here on my screen, so I moved it around just a bit. So here we introduce formally the bar graph. A bar graph displays the number or percentage of items in each category using proportionally sized bars. This can be used to graphically represent a categorical variable, just like a pie chart, or compare a quantitative variable across categories. The bars do not touch in a bar graph, except in a side-by-side bar graph, which I'll show you in just a moment. But still, the bars don't touch in between the major categories. In a histogram, the bars do touch, and we'll get to that later. It's called a frequency bar graph when counts are used, and it's called a relative frequency bar graph when percentages are used. So which type of bar graph is this on our screen? Notice that our vertical axis is the count in thousands for that same distribution of education. It's not a relative frequency. A relative frequency would be a percent or a proportion, a fraction. So this one is a frequency bar graph. We're using the count, the actual number of people in each category. So the height of the bars, the height of this first bar is 2,500, and so that's how many people were in that category. The web address for the following three graphical displays, these are variations on bar charts, is listed here in your lecture notes if you'd like to look at these closer or read the article that comes with it. This first example is called a stacked bar chart. Now, how's this different from the standard plain bar chart? Well, we can subdivide into other categories. Notice that we tilted our bars horizontally. So any bar chart can be shown horizontally. This just happens to be one example of that, where the bars are laying down rather than standing up. It's stacked because not only do we have these main categories here, notice the bars don't touch in those main categories. There's space in between the bars here. So the bars don't touch since it's a bar graph. However, they're stacked for different categories. So we have this yellow is don't believe, light green is believe but not certain, and dark green is believe absolutely certain. For millennials, the millennial generation, saying whether they believed in God. So that's a stacked bar chart. You can subdivide into more categories. Our next variation on a bar chart comes from that same article, that same web page. And this one is an example of a side-by-side bar chart. Notice this does the same thing as the stacked bar chart, only in a different format. So this article designer was trying to make his page or her page look interesting and not have the exact same type of chart in every single paragraph. So what does it mean to be a side-by-side bar chart? Well, just like the stacked bar chart, we have these main categories. Notice again that in between the main categories, the bars don't touch. However, in the smaller categories, again, your key is up here for who's who. In the smaller categories, they do touch. So in a side-by-side bar chart, main categories bars do not touch each other, that is. But the subcategories within a main category do touch. So that's another way to get a little more detail in a bar chart, a side-by-side bar chart. And our last variation on a bar chart would be back-to-back bar chart. Again, we can use the word chart or plot interchangeably. Bar chart, bar plot, whichever one you fancy. And this one shows approve versus disapprove by putting the bars back to back from each other. Just a different way to visualize the results. Now, I realize those other bar charts are not in your text, but you are going to encounter these in the everyday media, so I feel it's important to go ahead and cover them and show you guys what they are. Now on to pictograms. A pictogram is basically a bar chart where the bars are replaced by a picture. However, remember on the bar chart, the bars had to have equal width, so you could make comparisons of only the height. It's easier for our eyes to make these comparisons. It's difficult to keep the bar width the same in a pictogram because you distort the picture. So a plus of pictograms is they can be more visually appealing than a bar graph, but the minuses far outweigh the pluses, usually. They can be misleading because our eyes respond to the total area and not just the height. We can distort the pictures if we try to focus on what we should be focusing on, which is keeping that bar width the same across all three categories here, and only varying the height. So how is this pictogram on the right misleading? What's misleading about this particular graphical display? Well, it's exactly what we just talked about a moment ago. Notice that time spent roughly $4.5 million on advertising, and U.S. News spent roughly $1.5 million. 4.5 is about 3 times the amount of 1.5. So actually, time is only about 3 times bigger than what U.S. News spent. However, this picture, because we changed the height and the width of the time spending category, makes it look many times larger. So because changed the height and the width of the bars, which are really pictures here, it makes time look many more times larger than U.S. News, when it really isn't. Now introducing the line graph, otherwise known as the line plot. This shows a quantitative variable changing over time. It plots each observation against the time at which it was measured. Time will always be on the horizontal scale, and the variable goes on the vertical scale. We connect the data points by lines to display the change over time. So these are about showing change over time. Notice the graphic that we have here, the average price for regular unleaded gasoline from the Bureau of Labor Statistics. Again, I apologize, the layout's a little different than your notes. Hopefully you can keep up. What should we look for when we look at a line graph such as this? Well, the overall pattern. Notice that this does meet our criteria. Time is on the horizontal axis, and our variable is on the vertical axis. So what's the overall pattern here? Well, our overall pattern is a general uphill trend. We notice that in general, these prices are moving upwards over time. We look for any striking deviations. We would notice areas such as this one and right here. Anywhere it really dips or it really gets higher. An anomaly. And we would investigate why that happened. Usually with gasoline prices, it's politics. For striking deviations, we can usually pinpoint that to world situation. Seasonal variation is a pattern that repeats itself at known regular intervals, and we adjust many regular measurements for seasonal variation, like unemployment. It's definitely adjusted around Christmas time because our employment numbers would be inflated at Christmas because of all the seasonal workers. Do we have seasonal variation on our example of a line plot? Yes. And this is likely due, these are the little fluctuations that happen regularly, likely due to the fact that prices usually go up in the summer and down in the winter. Now we're going to discuss the area plot. Most places call this an area plot or an area graph. Some people refer to it as a stacked line chart, but this has multiple meanings. We really care more about how to read this thing. So the web address is here for where this area plot was taken. These are good for showing cumulative totals and for making relative comparisons across categories. Notice that this is a percentage that they are demonstrating here. And so all of our percentages should add to 100%. So this bottom dark green, the key says is for married. All right. And that is in 1960, 72% were married. The darker green is divorced or separated. So in 1960, 5% were divorced or separated. It's not 75%. It's just 5%, just a little piece of the area there that belongs to divorced or separated category. 9% were widowed, that's the lighter green, and 15% were in the never married category. So as you can see, it's good at showing the cumulative total. Here it's percentage, so they're supposed to add to 100. And it's good for making relative comparisons. We can see that this slice, 72, is much bigger than this slice, 15. However, it's not good for determining values for individual categories. Take, for instance, get rid of some of this. Take, for instance, the percent that are widowed in 1990. How would we figure that out? What percent are widowed in 1990? Well, widowed is the light green wedge. We can see that in our key. And 1990 is here. So widowed is going to be the length from there to there. This little light green wedge in 1990. Well, it's really kind of hard to tell what that is. Over here's 6, over here's 9. I can't tell if it's closer to 9 or closer to 6. Now we can pin it down somewhat, but it's not that great, as you can tell, for determining the exact amount in a certain category. So we have good and bad with it. So if you want to write something in your notes there about what percent are widowed in 1990, I'll write above it since that's what's on my screen. It's hard to tell because of the fact that it's not good for determining values for individual categories. Now, the next question that's coming up, which isn't showing on the screen, but it should be on your notes, is why do the numbers for 1960 add to 101? 72 plus 15 plus 9 plus 5 equals 101. Also notice that the numbers for the category 2010, 51 plus 14 is 61, 65, plus 6 is 71, plus 28 gives us 99. So these numbers add to 101, these numbers add to 99. This also explains why this top line, which should always be 100%, is actually fluctuating a bit if you take a look at this graph closely. It's actually fluctuating a bit. So why do these numbers add to 101 and why do these numbers add to 99? This is due to rounding. When they rounded the values for the individual categories, they left them where they were. They didn't fudge one category up or down just to make their numbers add up to 100. And this is very common in pie charts, bar graphs, any graphical display where you're using percentages. So the reason that these numbers add to 101 is due to rounding in the individual categories. when we round those numbers, they may not still add up to 100%. The histogram is a handy little tool, especially in the sciences. Histograms display quantitative variables. So when you have a data set of numbers, the histogram is one of the first things that you're going to be reaching for. One must be careful when choosing how to group together values. All the groupings must cover the same range so that the bars on the histogram are of equal width, just like the bar chart. The bars are of equal width. The height of each bin is how we compare the frequency or relative frequency of each range of values. Be careful that the number of categories isn't too large or too small. This can distort your overall message. Don't skip any categories. We'll look at one of those in just a minute. And be clear about the contents of each category. Our example is ages at the time of first Oscar. Okay, so taking a look at our histogram, it looks very similar to a bar chart, except notice the bars generally touch. The only reason that we don't have bars touching up here, in what we call the right tail of this distribution, is because there were no actors in that age range. But where we do have actors in that age range that increase the height of each bar, the bars do touch. Notice that on the horizontal axis, instead of having categories, we have groupings of quantitative values, groupings of numbers. This is what a histogram does. The groupings chosen here are written in this fashion. Remember that a square bracket means includes 20. So an actor that is 20 years old would go in the bin denoted by that one. But this bin would not include, with the round parentheses, would not include age 25. It's going to be in the next category right here because that has the square bracket on it. So you have to clearly define your categories of values. So let's practice how we would look at this. If Jack Nicholson, age 70, wins for Best Actor, which category frequency will increase? Well, if he's age 70, he's going to go in either this category or this category. Which one includes age 70? It's the one with the square bracket. Therefore, this category would increase by 1.